Hello and welcome to my YouTube channel. Today we shall be looking at ordinary differential equations that are reducible to separable equations. In our last lecture, we had dealt with equations that can be solved by the method of separation of variables. And we said that if we have equations of the form dy dx equal to f of y times f of x, or dy dx equal to f of y divided by f of x, then we can easily separate the variables of these equations, by writing y on the left hand side and x on the right hand side, then integrate and find the value of the unknown function. However, it is not always possible to have our equations in a form that is easily separable. So we are looking in this class or in this video at equations of the form dy dx equal to f of ax plus by plus c, where the right hand side is some function of x and y that cannot be easily separable or cannot be easily separated. So if we encounter such equations, we can reduce them many times or most times to a form that we can apply the method of separation of variables. To do that, we'll say let u be equal to the function ax plus by plus c, and then we proceed using our implicit differentiation to differentiate, and then it will now end up reducing the equation to a form that we can now handle. We shall now take an example, to illustrate the procedure. So we're asked to solve dy over dx equal to, in bracket, 4x plus y plus 1 all raised to the power 2. Now you would agree with me that if we expand this right hand side, for example, it would be now very difficult, to solve this problem by separating variables. In fact, it is nearly impossible. So here, we're going to make the substitution I had introduced earlier to help us reduce this equation to a form that can be separated. So we say, let u be the function inside 4x plus y plus 1. And this is how we start. We now differentiate both sides of this equation with respect to x, since x is the independent independent variable here. So we differentiate both sides with respect to x, and we get du over dx is equal to, differentiate 4x, you get 4, plus differentiate y, you get 1. Since it's a function of y, we get 1 times dy over dx. Differentiate 1, you get 0. So if we make dy dx the subject of formula here, we get that dy over dx is equal to du over dx minus 4. So I call this equation, the original equation 1, I call this one here 2. So the original equation 1 now becomes dy over dx equal to, since u is now 4x plus y plus 1, so dy dx now becomes u squared. So if I call this guy equation 3. But from equation 2, dy dx is du dx minus 4. So I could just replace dy dx here with this, and that becomes du dx minus 4 equal to u squared. So that du over dx now becomes u squared plus 4. Or if you like, we can write du over dx equal to 4 plus u squared. Now, call this equation 4. Equation 4 is now in a form that can easily be separated in terms of variables. So, if I say this is over 1 and cross multiply, what do we get? We get du times 1 is du equal to 4 plus u squared times dx. So if we divide both sides by 4 plus u squared, we now have du over 4 plus u squared equal to dx. And with this, we have separated variables. So that the left hand side is now in terms of the variable u, and the right hand side is now in terms of the variable x. So we have now transformed our original equation, which was given in terms of y and x, to now u and x. So we shall now solve for the value of the unknown function u. So we integrate both sides. If we do that, we have the integral of du over 4 plus u squared equal to the integral of dx. Now this left integral is a familiar integral, and if you integrate the left hand side of this function, what you simply get is 1 over 2 tan inverse of u over 2 equal to the right hand side integral gives us x. We now introduce, of course, our constant c of integration. What we want to find is the value of the unknown function u. So if we multiply through by 2, we get the tan inverse of u over 2 equal to 2x plus 2c. So if I write this as the tan inverse of u over 2 equal to 2x plus say c1, of course, where c1 is equal to what? 2c. I want to find u. So since tan inverse of u over 2 is equal to this, it follows that u over 2 must be what? The tangent of 2x plus what? C1. Since tan 2x plus c1 is equal to u over 2, it follows that 2x plus c1 is the tan inverse of u over 2. So this means this. I want to find the value of u. So my u now becomes 2 times the tangent of 2x plus c1. I've solved the problem now in terms of u, but the original integral was given in terms of what? Y. So we must go back to where we came from. So we have here that u is equal to 2 tangent of 2x plus c1. But what is our u? Our u is 4x plus y plus 1. So u here is 4x plus y plus 1. And that is equal to what? 2 the tangent of 2x plus c1. We want to find the value of y. So we send 4x and 1 to the right hand side. So we have that y is equal to 2 the tangent of 2x plus c1. 4x to the right becomes negative 4x, and of course plus 1 to the right becomes what? Negative what? 1. So we have now solved the original differential equation, which was not separable. We have reduced it to a form that is separable over here, and we have applied the method of separation of variables to solve the equation. And our solution is y equal to 2 tangent into 2x plus c1 minus 4x minus 1. And of course, if this problem was an initial value problem, we would have been given an initial condition at this point, which we would have used to determine the value of the constant what? C1. As an exercise, try to solve dy over dx equal to x plus y minus 1 over x plus y plus 1, and leave your answers in the comment section below. Please subscribe to this YouTube channel and kindly share, like, and drop a comment. Thank you, and bye-bye.